Hey guys, I've got a new problem for us. So my cousin was a really big weightlifter back in the day, but then he had a car accident and he lost his arm.
Oh.
Yeah, it's a bummer. But he wants to get back into it, and so he's come to me with a very interesting problem. He wants to get back to his max deadlift of 300 pounds, but he wants to do it with a prosthetic arm that he 3D printed himself.
So it wouldn't cost him an arm and a leg?
Yeah, sure, something like that. So what do you guys think? Is that something we can do?
Super cool idea, but I think we should add a safety factor.
Probably a good idea.
Yeah.
The machine that we got to test the samples is called a Tensile Tester, which has a max X capacity of 50 kilonewtons with an accuracy of 0.5.
To record the length and thickness, we're going to be using digital calipers with an accuracy of 0.1 milli-inch.
The expected outcome of our experiments is the determination of the Young's modulus of the PLA specimens with different infills, based on the stress-strain diagram. These are the key concepts that we're going to use. Firstly, to quantify the total uncertainty, we use the RSS method, which is based on the bias and precision error. Moreover, we apply uncertainty propagation to obtain the total uncertainty, the modulus of elasticity. Since our sample is smaller than 30, we use a student's t-distribution to analyze our data. To remove all outliers, we apply Chauvin's criterion, and chi-squared analysis help us verify that our sample is a Gaussian distribution. In order to obtain the Young's modulus, we have to measure variables like the force from the tensile tester, the width and the thickness of the specimen, and the initial and final length of the specimen with a caliper. For the 10% infill specimen, the Young's modulus is 633 megapascal. That is going to be the lowest value, because when the infill goes up to 100, the Young's modulus is going to reach around 3000.
I think that the higher the percentage of infill goes, the more elastic it'll be, because there's more material there to resist just this brittle break that we have.
To ensure accurate determination of Young's modulus, we evaluated multiple design alternatives for specimen preparation and testing. For infill pattern, we tested grid and gyroid structures. The grid offered consistent force distribution. However, we chose gyroid because it showed better results for the tensile test. For test method, we compared direct tensile testing, flexure testing, and compression. Tensile testing was chosen because it's first-order response and direct modulus calculation. For material, we compared PLA, ABS, and PETG. PLA was selected because it is more cost-effective while still providing sufficient mechanical strength and stiffness to meet the project's performance requirement.
In our research, we found that it was not necessary to use the chi-squared test to determine goodness of fit of a normal distribution. This is because there was such a small value of samples per infill percentage that it was more relevant to use the student's t-distribution to accurately represent our outliers and our uncertainty.
While we tried our best not to allow any error to creep into our experiment, we found a few areas in which it might have, the first being in the precision. Each sample had a small amount of difference in its dimensions. We also tried to load the sample in the same every time, but there could have been slight differences in the way that we did it. The tensile tester, when zeroed, would wander around zero with the force. Our calipers were also only accurate to the third decimal place, and the tensile tester was only accurate to the fourth decimal place. If we had any bias, it came from the instruments not being traceable to the known standard. To determine the true mean for each infill percentage, we used the student's t-distribution, since each infill percentage only had 7 samples. From this, we were able to determine that our degrees of freedom were 6, and our confidence interval we decided was to be 95%. Using this, we were able to say that we are 95% confident that the mean modulus of elasticity for each infill percentage lies within the ranges shown.
I'm going to talk about soberness criterion for outliers. First, we are going to use a confidence of 95% because it is the industrial standard. Next, we are going to obtain Dmax that represents the allowed band around the mean. In our case, is 0.91. The next formula, where x is the suspected outlier, x bar is the sample mean, and Sx is the sample standard deviation. If that value is smaller than the max, we keep the sample. Otherwise, we discard it. That's why we have created a table in Excel where the yellow boxes are the outliers.
The uncertainty propagation of this sample was found by using the sensitivity equation, or the root sum square, of all of the partial derivatives multiplied by the associated uncertainties. Using a sample point printed at 70% infill, we found that the propagated uncertainty was equal to 45.88 megapascals. This was consistent with the values found using the z-table. Therefore, we can conclude that the z-table values are accurate and can be used along with the student's t-test and Chauvinet's criterion.
Conclusion. First, we have to define the characteristics of the problem statement. James' cousin wants to lift a weight of 300 pounds. If we apply a factor of safety of 2, the weight is going to be 600 pounds. We do this because we want to make sure that the arm is secure and reliable. In that way, the force is going to be around 2600 Newton. We are going to use an elongation of 0.01% of the length to make sure that the arm doesn't deform too much. The area of the arm is going to be 0.049 meters squared, since we consider that the arm is a circle that has a diameter of 0.25 meters. Finally, the Young's modulus required is going to be 453 megapascals. That is the result of dividing stress by strain, and the stress is force divided by area. In the right, we can see a chart with the mean Young's modulus for each of the infills. The chosen infill is 40%. But why? First, because the Young's modulus is higher than the minimum requirement of 453 megapascals. However, from 40% to 100%, all of them meet this requirement. However, we choose 40% because it is the most cost-effective option, since it uses the least material of all of them.